Dr. Narayan is co-founder and CEO of Morphing Machines India. Dr. Narayan and team are building a multi-core processor to enable businesses to build energy efficient high performance systems. Her innovation focuses on Redefine, which is a processor indigenously conceived, developed, and implemented in India. It's an excellent replacement and upgrade for CPUs and GPUs from multinational brands. So her talk is going to be on domain-specific architectures and reconfigurable computing. So, Dr. Narayan.
Thank you for this opportunity. Good morning, good afternoon, good evening, as the time zone, as appropriate to the time zone. And I'm very excited to be in this symposium E4R, and what our contribution is probably research to engineering. So my topic for today is domain-specific architectures and reconfigurable computing. And I would like to mention that this is a story from India. And it started at the Indian Institute of Science, one of the top research institutes of India and the world. I, being an alumnus of Indian Institute of Science, as well as my colleague Professor Nandi, incubated morphing machines at IISc, and we wanted something, a processor which reconfigures itself. And so we named the company as Morphing Machines, the machines that morph themselves, and our processor architecture is called Redefine. So without much ado, so I already said where Morphing Machines was born, and it's an independent company now. It's a fabulous semiconductor company based in Bangalore. And we are focused on innovating processors for heterogeneous computing on the same chip. Redefine is the name of the processor. It is massively parallel. Very important to note that it is runtime reconfigurable. It's a many core processor. We'll know more about Redefine as we go through this talk. So I would like to outline this talk saying, what is the problem that we are looking for? There are COTS processors that are available, that have been available. People are happy about it. But what are the actual problems that people are facing and will face going forward? What's the solution that we are offering? Talk how we are doing it by talking to you about what is this redefined processor about. More importantly, the redefined compiler. During the opening remarks and the introductory talk by Dave, he did mention that compiler is one of the crucial components to make use of everything that a metal can offer. Metal can offer many things, but somebody has to enable it. And the secret sauce is the compiler. And we will talk. I have 1 or 2 slides about the redefined compiler, where the compiler says, this is what the metal has to do to get the maximum out of it. I'll also share with you power performance area of Redefine and how Redefine is suitable for heterogeneous computing. So without much further ado, so there has been a lot of improvement in the processor architecture over the last 4 or 5 decades. Initially, it started with supplying redundant components for potential failures of processors and other electronic systems. Slowly, it matured into architectural improvements, both in terms of basic architecture of the processor, as well as the emergence of multi-core processors. Why did people start looking at multi-core processor? Because we had to cater to the mixed workloads. Take an example of avionics. So it has critical workloads as well as non-critical workloads. So that's one of the reasons why multi-core processors started emerging into the avionics segment. And as we treaded into the 2000s and onwards, there was emerging applications. Even when you talk today, there are applications which are very challenging for the hardware today. For example, the 5G and going ahead, the 6G applications. So what we have today and what we people are thinking about is to put together and integrate multiple processors from multiple vendors on a single chip. So there are not on a single chip, on a single system. So there has been tries of heterogeneous integration, but it comes with its own challenges. For example, are we able to segregate applications that run on different processors? Then the end user has to be familiar to use the varied software tool chain to make the processors work the way we want. And this has been the challenge. And also, because we use heterogeneous processors, are we really segregating and making the computations secure? In fact, if you look at one of the air crashes, uh, it has been a problem of not identifying a software bug. Not that people were not doing their jobs, but it's a very challenging thing that led to air crash. Air crash. So the basic root causes of the problem, in my opinion, is that COTS processors can only partially address the objectives of the application. It could be power, it could be performance. That's because we are looking at mixed critical loads. Also, when we use COTS processor today, it is not very deterministic to say, what is the latency going to be, what is the throughput, what's the power it's going to take. Also, if you look at the way COTS processors are used, the movement of data in and out of chip, the movement of data within those chips are also very insecure. So having recognized the problem, now if you look at the root causes, see, COTS processors are there, and then you get a system, but you have to build layers of software for applications to run. In other words, the application itself needs to tread all those layers before getting executed on fixed hardware. This is one of the reasons for non-deterministic behavior of applications. Now, our question is, how do we address it? The other root cause is the way the data is input, the way the data is processed, and the way the data is used. It leads directly to breach of security. So these two root causes were actually the motivation for us. And we said, can we address these two root causes? So we started conceiving about Redefine. So, and also we know that the number of the software layers, the number of software layers an application has to trend has to be as minimal as possible, if possible, zero. So what we did was to define domain-specific architectures in software. So in other words, software defined domain-specific architectures. Nothing but the compiler defines the domain-specific architecture, produces metadata, it defines the DSAs, but the runtime takes over and obeys what the compiler says. And this is from the angle of the software. And we need to have a hardware, which is a single hardware that can support diverse DSAs, also providing the expected power performance and security and segregation. So these were the motivational factors. And also, traditionally, we have been using one paradigm of computing, which is PC driven. So you know the sequence of instructions that are going to get executed. But because of the background of that many of the people in the team had, we have adopted what we call the data flow execution paradigm, which is not an invention by us. It is invention way back in 70s. And we have adopted the data flow execution paradigm at a macro level so that we restrict the movement of data within the DSAs when the DSAs are getting executed, and also make sure that the data movement within the DSA stay as close as possible. So we came up with our processor architecture called Redefine, and the good part of it is it's post-silicon customizable and runtime reconfigurable. So how do we do this? I think I already touched this point. We use our compiler to compile applications to domain-specific architecture. Our compiler optimally identifies the resources that are required for an application and also the inter-resource communication pattern. All that is determined by the compiler, but the whole thing is managed in hardware at runtime. So the applications just get implanted on our execution fabric. There is no software that runs between the application and Redefine. So the executable again are defined, as I mentioned already, defined in software. It exposes multi-scale, multi-level parallelism. It's a very hard problem, but we have been lucky to come up with our own compiler, of course, using the LLVM infrastructure. Some of the passes of LLVM we use. And the beauty of Redefine is we have a distributed power control. So at the compile time, we can provide hints to the hardware to control power. So whatever the compiler tells the hardware to do, the hardware is going to do. So there are lots of COTS processors available today, and each one of them have their unique good features. I'll just touch upon just a couple of them. For example, if you take the general purpose processors, they're very flexible, easy to program, cost effective, of course, but are they good in power? The answer is no. Are they customizable? The answer is no. Then came the era of GPGPUs and FPGAs, the field programmable gate arrays. There, you know that GPGPU are very good. They are flexible, quite easy to use. They give good performance, but they're power guzzlers. Then if you go to the field programmable gate arrays, you can customize FPGA as though it is behaving like an ASIC, close to ASIC, but then they are very difficult to program and use. So these are the axes we used to come up with our architecture, and we believe that we derive the maximum in each of those dimensions. I don't claim that we could as good as GPUs in certain dimensions and as good as the general purpose processors in some other direction. So with that, what we do is we will look at just, this is just one slide to say, where Redefine is going to find its place. If you look at avionics, that's how our story started. Morphing Machines got engaged with one of the leading aerospace companies. And then the architecture and the compilers toolchain started to build. This was avionics, and avionics is looking at integrated modular architectures in which they want to put different kinds of processors together, so that it is not only it is not only the cost saving, but also they wanted something that the architecture needed to support secure computing, more importantly, redundant computing. That is because the avionics industry especially has multiple copies of the same application running on the hardware, so that they take the majority vote and go ahead and take decision, because it's a very crucial piece of software that need to run. Also, avionics demand that some of the applications need reactive processing. There is some sensor data comes in and the aircraft has to immediately react. So our engagement with Safran has yielded what is Redefined today. Now, if you look at the automotives and industrial automation, I would not call it a subset, but many of the problems that we try to solve for avionics is true in automotives and industrial automation. For just benefit of time, I will not go into details, but the problems and the applications that we look at in avionics and automotives are more or less the same. If you go to telecom, again, coming of age of 5G and 6G, there are a lot of AI ML processing workload that are going to be at front hall, mid hall, as well as back hall. And that's one more space that we are looking at. And also managing the network itself. And Redefine being a massively parallel, scalable architecture is very good for HPC for both data analytics as well as training. And one day we are starting to engage with the HPC, the HPCs as one of the end customers. Now, a peek into what Redefined looks like. It's let me go and see if I can. Yeah, yeah. So if you look at this slide, a redefined node, basic node, is made of multiple number of cores. In this example, it is 4 cores. And each core is capable of supporting one more core called the custom function unit. So suppose you want to really speed up, let us say, you're doing some DSP kind of, you're targeting Redefine for DSP kind of applications, you may want to put in an FFT there. So the blue boxes there are the custom function units, which can be tied to each of those cores. The cores themselves are based on a subset of RISC-V ISA, simple for us to use, but we need to supplement the RISC-V ISA with our own specific instruction, redefined specific instructions. That's because we need to make sure that we provide that facility to the application writer so that he makes maximum out of Redefine. So that is what each core of Redefine looks like. And the good part is each Redefine node has its own power control, and any node that is not in use at runtime can be switched off. And this is how we meet the power objective. Another good thing is the green box that you see out there, which is a memory that is associated with each node of Redefine. Again, we make sure that maximally the computing, the the instructions and the data that the instructions use lie within a node. How do we make sure? Our compiler tries to do that. Remember, I said our solution is to keep the computation close to the memory, and this is one of the jobs that the compiler does. So each redefined node looks like this, and we have a simple 2D mesh toroidal topology to connect several such redefined nodes. And this is an example of a 256 core redefine, and you can see that it is scalable, regular architecture, completely distributed memory. One important component is the brown box out there in each of those redefined nodes, which is the orchestrator. So the orchestrator sitting inside each node is going to orchestrate all the computations and memory accesses that it is responsible for. So this is the very, very high level look of Redefine. And what you see on the right is the block diagram of Redefine. And as I speak, we have dropped off the RTL to the backend design. And that's where we are today. In a month from now, we should be able to completely characterize Redefine. So let me, and Redefine acts as an accelerator to a host, and we are agnostic to the operating system that runs on the host. What we do is we develop device drivers and then use Redefine as the accelerator. So if I go to the next, okay, this is the initial placement and routing of 64 core Redefine. It is not yet optimized, and our initial numbers indicate that a 256 core Redefine in 28 nanometer technology is going to occupy approximately 160 squared in 28 nanometer technology. So I just wanted to share with you the initial placement and routing. of a 64 core redefine. Now, coming to the one of the important aspects of our technology is the software toolchain. As I mentioned earlier, Redefine acts as an accelerator to a host. So, if you see the picture on the left here, the host, the end user application consists of two major parts: the code that needs to run on the host and the code that needs to run on the accelerator. They go through our compiler, and the host code compilation makes sure that all the code that needs to run on the host get compiled into the executable of the host. And then our compiler, the redefined compiler, takes the kernel code. I'm calling it kernel to use the terminologies that GPU use, and compiles into kernel binary that can run on redefine. So again, the bottommost picture on the left says how the host processor and redefine talk to each other. It is through the device driver and the runtime that makes this happen. Now, talking a little bit about our compiler, which is our secret sauce. As I mentioned earlier, we plug into the LLVM framework and use lots of passes that LLVM offers. That has been a good thing. What we did initially, again, I'm going to recollect what Dave said in his introductory talk. We have our own domain specific language. Okay, we call it C with hyperops. Forget the name for a minute. But if a end user is going to program his application in our DSL, he is going to get maximum out of redefine. So the application written in DSL, we use, as I said, we use the LLVM infrastructure, but have our own redefined specific passes for all that is indicated here. And then we modify the LLVM backend to spit out a redefined executable. This is one part of the compilation flow. But not, we cannot expect everybody to write their applications in DSL. It's a little hard, but then, and also we want to support the legacy applications and applications that people are more comfortable with, the OpenCLC. So we have the compiler for OpenCLC. We again use some of the LLVM passes, make sure that we generate the code that our backend understands. One of them is the intermediate representation that we use internally, and we finally get the redefined executable. And as I speak, uh, because we are looking at AI ML applications, it is best to support TensorFlow and PyTorch and programming frameworks that like that. And by the end of March, we expect the complete flow from TensorFlow to redefine executable. Right now, we have the first version, but then it is not optimized. We would want to drop in TensorFlow programs, get it translated to our DSL, and take this path again to make sure that we make maximum out of redefine. So this is our secret sauce. And with that, let me go and tell you what we do. So in this example, you have I've taken an ADAS example very consciously. That's because three example kernel. One is a streaming kernel where data continuously comes in, can redefine supported. Another example is a low latency kernel, for example, collision avoidance. And the third one is an anti-lock braking example, which expects response moment an event is there. Whether redefine, I claim that redefine can is good for reactive applications. So consciously we have taken these three examples. It's very interesting to note that all these kernels use the same compiler to generate the redefine executable. And what does our compiler do? It specifies the designs, sorry, domains specific architecture for each of those kernels. For example, a DSA for a low latency kernel would, would want to have as many compute resources as possible so that the latency is low. Whereas for a reactive kernel like anti-braking, we have to make sure that the kernel stays on the execution fabric, but wakes up moment there is sensor data. How do we do this? As I mentioned earlier, we follow a macro data flow execution paradigm. And for us, data is the control. And so if there is an indication of a collision, that data goes as the control to wake up the DSA for K3. Okay, so that's how the reactive kernels get executed. And the other example I was talking about is a streaming kernel, where again the DSA is produced by the compiler. We make sure that we exploit the pipeline parallelism that is available in the streaming kernel. So it's interesting to see that we use the same compiler for different kinds of kernels and plant them at runtime on Redefine. So I've tried to bring out the niceties of Redefine in this slide. For example, we talked about in integrated modular avionics, we have to have redundant kernels or multiple copies of the kernel running at the same time on the fabric. So what we do is we instantiate multiple copies of them. This is again, I can't go into details here, but our execution paradigm really aids us to do this. So let us say, there is one kernel, kernel K2, that's running on particular portion of the fabric, and some of the resources there or one of the resources fail. So what do? We gracefully migrate from that portion of execution fabric to some other portion of execution fabric. How are we able to do it so gracefully? If you look at the DSA of any kernel, we have created a virtual region around that kernel. That's because our compiler has said that these are the number of resources you require and no more. All your communication is within that space, and you use those communication memory and computation resources to execute your kernel. Runtime system of Redefine is not at all going to disobey what the compiler says. And so even when DSA of K1 is running in some part of the execution fabric, we are sure that the unused portions of the fabric are healthy, and so migrate those that failed kernel to healthy resources. So this is the runtime reconfigurability of Redefine, which I mentioned right in the first slide. So this is the dynamic reconfiguration or runtime reconfiguration. And also make sure that the system is highly available. A couple of other things to note that is that whenever a kernel finishes execution, the portion of the resources are freed and they can be reallocated in any which way, as the compiler says, to some other kernels. So again, I'll take the same picture to tell you, now you can see how the kernels are segregated. Each kernel is executed in its own safe region. And I've talked about how highly available Redefine is. And it is a dynamic allocation of resources on the execution fabric. So we are able to consolidate the heterogeneous processes on the same single chip. So these are some of the numbers, that power performance area numbers we have. We have our own simulator built in-house within Morphing Machines. So we can simulate up to 48, or sometimes, if the applications are small, we can simulate up to 64 cores of Redefine. And here I've indicated, and some of these power and performance numbers we are obtaining from the backend design as I speak. And in this table also, you can see that since Redefine is a scalable architecture, but then we use the same software tool chain, uh, an end user who wants to use Redefine in the HPC space has the same comfort as a person who is using it for an edge device or a handheld device. They all they need to know is how to use the Redefine compiler and the associated tool chain. So this is a qualitative graph that says, how we stand vis-a-vis the other offerings in the market, the general purpose processors, the GPUs, and the FPGAs. As you know, GPUs are very good in performance, but then they are limited by two things. One is the shared memory. So many of the computations which need to uh, use memory need to go and access the shared memory very often. Penalty two ways. One is high power and high latency. And other limitation of GPUs is the data parallelism is very, very, very well exploited in GPUs are meant to exploit data parallelism. At best, we can do just as good as GPUs. That's a disclaimer. However, for task level parallelism, I would like to go back by two slides here. For task level parallelism, each of those resources which are allocated to a particular kernel can be doing something different from its neighbor. We exploit task level parallelism in Redefine, and that's one of the reasons why we say, and it's measured and of course computed performance, that our G flops per mm squared is better than GPUs. We are taking into consideration here both applications which exhibit data level parallelism and applications which exploit task level parallelism. Okay, again, I showed you the high level diagram of Redefine in which we say, there is a power control in each of those Redefine nodes, and we have the ability to switch off resources which are not in use, number one. Number two, since we create a nice secure virtual boundary over each of those application kernels, we make sure that we stay within that boundary, which again leads to low power consumption. And I already gave an example of runtime reconfigurability. Some of the features we come close to FPGAs. However, because we are providing you support for high-level languages, OpenCLC and TensorFlow as we speak, but then any other language that we want to support, we need to build the front end and drop it into our compiler framework. So it's easy to use Redefine. And so this slide captures the qualitative comparison of Redefine with the other COTS processors. So this again is an example. How much time do I have? About 5 more minutes?
Yes. Yes.
Yeah. Okay. Yeah. Okay. Okay. So this is a slide in which we are depicting something. For example, if you take a Tesla, there are different kinds of processors which are used for different kinds of processing there. For example, there is sensor data that's sent over to the general purpose processor, the Cortex, it preprocessor, and then GPUs have their own applications that need to run, which show high SIMD kind of parallelism. GPUs are the best for that. However, for some of the AI ML applications, it is the neural processing units that they use. What we say is, since Redefine is runtime reconfigurable and also post-silicon customizable, we can use the same processor for the different applications which show heterogeneity. And we did a paper and pencil computation, and then we also compared it with NVIDIA A100. Our on-chip memory allows us to have for Redefine to be used, large Redefines to be used. For example, 4096 core redefined or 10024 core redefined for big data analytics, training, basically training in the HPC segment. And that's because we need to have lots of weights that need to be on chip. If we go off chip to fetch the weights, again, we are going to pay in terms of penalty in terms of both power and latency. And the table, the right bottom shows the comparison between Redefine and NVIDIA A100. Again, I have talked about the various aspects of Redefine, which are all captured in the left side of this slide. So with that, I think this is my last slide. So I think I've talked about all of them in the different slides. So this is the summary slide where we say that, yes, we exploit fine-grained parallelism. For example, let's look at this. As I said, SIMD, great. GPUs are really great. We can perform as good as GPUs. Whereas if it comes to task level parallelism, GPUs croak. And these are the application areas we are looking at for data analytics, especially graph analytics and things like that. And we are able to exploit pipeline parallelism because our DSAs stay on the fabric and we can communicate the intermediate results within the virtual region. We don't have to go to main memory and hence lose in terms of secure operation as well as the penalties we pay in terms of time. Already given you an example of event-driven support for event-driven applications. And one of the driving factors for this has been the avionics industry, our customer, who is Safran. So, and so there are, and we can dynamically reconfigure resources, which makes it highly available and resilient. And as we speak, we have support for OpenCLC, TensorFlow, going into very short future, PyTorch and other front ends of interest. And to start with, as I said, DSL is the choice, but then we already have support for OpenCLC and PyTorch. So, and we definitely believe in supporting legacy applications. So today we have support for legacy OpenCLC applications. So with that, I thank all of you for giving me this opportunity and open for questions. Thank you.
Thank you, Dr. Narayan. I really like the examples you gave from the automotive industry, because I mean, here in Germany with lots of OEMs and everybody speaking about how they want to add features and change the software. It's just not possible anymore to have an ECU or an SoC like completely fit to this one thing they want to do. So this opened up a new perspective for me. Ashok, what are your thoughts?
Well, it's I think the fact that it was actually possible now to think of reconfiguring hardware at that level is something that was just news to me. I mean, it wasn't even something that I was aware of. So thank you. Thank you for actually taking us through this amazing story. We had this thing, maybe time for just a couple of questions from audience. One of them is, are there any other solutions? Is this like a completely new area or approach that is there about software-defined hardware, or are there other such examples like Redefine where people are looking at ways to solve this problem?
I'm not saying that we are unique in the world. That's not true. That's not true. But we have certain features. For example, the migration of DSAs without disturbing that's because we really draw the virtual boundary. That is one of the key things that we have. And what we did was we approached this whole problem from both the compiler and the architecture perspective. So the last leg of a compiler is very, very crucial to what we do. What I said, the metadata that the compiler produces. So some of the architectural features has helped us to to address some of these problems. Because we went back and forth between the compiler and the architecture to make sure. And the important thing is our initial engagement with Safran really helped us, because we were looking at the requirement from the customer point of view. To answer your question, yes, there are architectures, but they're a little more restrictive, and also the execution paradigm that we have adopted gives us some natural benefits. For example, unless we have data, we do not start computing. So that sort of reduces some of the load on the compiler. For example, producer-consumer relationship, how they have to be ordered, they all come naturally. It is one of the things that people have tried to do, and then at a micro level, micro data flow level, the overheads are too much. That was the topic of my thesis. And so we adopted a macro data flow level of execution. People have definitely tried various things, but I think what we have been able to do is put things together. And as I said, we have simulators running, but then our MPW should come out, the prototype chips should come out 12 to 14 months time from now, but that's where we are today.
Okay, great. Thank you for that. There were also just a couple of other questions around. You had mentioned it's in use already. Like you had mentioned, you have an avionics client already using Redefine. I'm assuming for some of the other use cases that you had mentioned, especially around like AI ML applications and around high performance computing, they are in the works, given you had mentioned you are targeting, like trying to make it more available for language like TensorFlow and so on.
Yeah. So I see a couple of questions. That is whether Redefine is commercially available and whether we are building it. So to answer those questions, yes, as I speak, we have the soft IP, but we have to, we are applying the last mile, and then we have to make sure that we characterize it properly. And our prototype chips will be available 12 to 14 or 14 to 16 months from now. Compiler stack, again, we need to optimize a lot of things, which we are doing it, and then go to chip production sometime, late 2023. That's late next year. So that's where we are. However, having said that, what we are doing in the next 2 months is 2 to 3 months, I would say, is to provide application development kit of Redefine. So as I speak, what we have is the soft IP getting fully validated and verified and put on a small FPGA board. I won't call it small. That board can hold up to 128 core Redefine. And we want to give that along with the software stack to the end customers, maybe for POCs, and then handhold the customers and develop applications for them. And also we have the liberty to little bit, I won't say the design, but then we can incorporate and customize Redefine for that particular user. For example, one of the benchmarks that we have got is from Bosch, and that's what has made us really go full speed into the supporting TensorFlow. So we are coming back to the application development kit. In a couple of months time, we should have the application development kits, and we want the end customers have a close tie with them, go for POCs before going into MPW. That's one of them.
Thank you so much for that. Really enlightening. And I just learned so much today. I think we are there may be a couple of other questions. If you could, if you have some time, please do answer them on the chat.